Okay, Andy. So we have our rotation matrix up here. We have phi in the I think I did a screencast on this, but phi is going to be around the z-axis, theta is around the y-axis, and psi around around the z-axis. Well, yeah. As we start with this, it's around the z-axis. That's talked about in my earlier screencast. So now we have which direction these are going. So this is always going to be in the z direction. This is actually going to be around the, depends on how the phi axis works. So it varies. It's from phi goes from 0 to 90 degrees. So we can model it with just this. And this is going to be wherever the new z-axis is when the thing rotates. So that's why we get this. So we can model it by how fast it's changing and in which direction it's going. That's how we can get an omega. And to make it easier, we can do it omega from the frame of whatever we have tumbling. So we get this. So we have whatever we have. We talk about this pound in class. Find the center of mass. General formula. Then we have this moment of inertia tensor here. I'm not very good at matrices, so this is how I did it. And then we have the moment of inertia. So the cool thing about it, for the tensor, this is what it was with these plots. First of all, we're assuming that everything has a mass of 1, all these dots or whatever that we're using. Otherwise, you have to put a little m around all these terms. So we have, alright, tensors. So the tensor, the cool thing about that is that the tensor times omega is equal to the eigenvalue times omega, so it can give us how it's going to rotate, because this is all based on angular momentum, right? So angular momentum is equal to tensor times omega, which is also equal to the eigenvalues, values times omega. So that's pretty cool. So we go on here to then we can do kinetic energy of the body. So we did a screencast on this. It's pretty much just some bunch of algebra with the cross products of angular momentum. So bada bing bada boom, and I can do the Euler-Lagrange equation, which we don't need potential energy for because this body, if you can use my mouse for this, the body's coming and it's tumbling. I can't make my mouse spin around, but it's tumbling as it's going in a straight line. But the center of mass, it's not actually changing, so potential energy doesn't actually change. We don't have to do the we don't need to do the kinetic energy minus the potential energy, yada yada, for the Lagrangian. We just plop in kinetic energy. So then we get this stuff, and then do your normal ND solve command and normal manipulate and the time, and there's our tumbling object.